As we all know, Father Christmas delivers a large amount of presents to a lot of people each year. Each present is going to have some form of mass, and all of these presents will amount up to a large amount of mass in one place at one time. So the question we're asking today is, will these presents have any effect on the length of the day? Some assumptions we're going to make for this video are that Santa makes 2 presents for every person on Earth, and each present weighs about 10 kilograms. So that is 7.8 billion people on Earth, 2 presents each 20 kilograms each. That's around 156 billion kilograms, all in one place at one time. We're also going to make the assumption that the Earth is spherical. In reality, it's an oblate spheroid, but for this video, we're going to assume it's spherical to make calculations easier. And finally, we're going to assume that the effects of tidal forces from the moon don't come into play here, so the Earth is isolated from the moon and therefore angular momentum can be considered conserved. So the first thing we need to consider is, how do we measure a day? Well, there are actually 2 types of day, which you probably weren't told in school. There's the solar day and the stellar day. Now, don't worry too much about these for the time being. Just know that we're talking about a stellar day in this video, which is the amount of time the Earth takes to do one full rotation. So rotate through 360 degrees once, which actually only takes 23 hours, 56 minutes and 4 seconds. So not the full 24 hours, because we look more at solar days when we get 24 hours for that. So remember, 23 hours, 56 minutes, 4 seconds for one full rotation of the Earth, which is 86,164 seconds. That number will be very important later on. So how long is a day? It's 86,164 seconds for this purpose. So how does mass then affect the Earth's rotation? Well, to understand this, we need to understand 2 things, one of which is rotational inertia, the other is angular momentum. So rotational inertia is a property of any object that can be rotated. It tells us how difficult it is to change the rotational velocity or angular velocity of an object about an axis. So the rotational inertia depends on the mass of the object and how the object's mass is distributed. And it can be calculated using the equation I equals to mr squared, where I is the rotational axis, m is the mass, and r is the distance from the rotational axis. As I mentioned previously, we are considering the Earth as a sphere. And now for a sphere, the rotational inertia is calculated slightly differently to the original equation. In a sphere, the rotational inertia I is equal to 2/5 mr squared. Again, where m is the mass and r is the distance from the axis of rotation. The axis that the Earth rotates around is a line that goes from the South Pole through the centre to the North Pole. The next thing we're going to talk about is angular momentum. Now, we've heard of momentum before. It can be thought of as mass moving. A very simplistic way to think of it is mass moving. It's calculated using the equation rho equals mv, where rho is the momentum, m is the mass, and v is the velocity. Angular momentum is just the rotational equivalent of momentum, and it's calculated using the equation L equals I omega, where L is the angular momentum, I is the rotational inertia, and omega is the angular velocity. So let's consider what effect Father Christmas's presents would have if Father Christmas had originally chosen to live on the equator, which is the furthest distance from the centre of the Earth, or the widest part of the Earth. So the first thing we need to do is calculate the angular momentum of the Earth. And to do that, we need 2 or 3 equations. We need the first equation, which is that of rotational inertia, which is 2/5 m(e)re squared, where the E stands for Earth in this case. We also need the equation for angular velocity, which is omega equals 2 pi f, and of course f is 1 over t, so that means omega is equal to 2 pi over t. And this is the equation for angular velocity. And finally, we need our equation for angular momentum, so that is L equals to I omega, where again the I is the rotational inertia and omega is the angular velocity. So this is our angular momentum equation. So if we substitute our I here with the equation for rotational inertia and our omega with the equation for angular velocity, we get 2/5 m(e)re squared times 2 pi over t. Now this can be simplified to 4 pi over 5 MERE squared, so that's 4 pi over 5 times the mass of the Earth and the distance from the origin of the Earth. Subbing in our values then, we get a value for the angular momentum of the Earth of being around 7.07 times 10 to the 33 kilogram meters squared per second. As I said earlier, we are going to isolate the Earth from the tidal effects of the Moon, which allows us to keep the angular momentum conserved and therefore rearrange the equation to find the angular velocity and therefore the time period that the Earth takes to do one full rotation. So we're going to take into account then what would happen if we add the Santa mass to our original mass. So that means our MES, or our mass of the Earth with Santa, is equal to our mass of the Earth plus our mass of Santa. Then getting our equation then for angular momentum again, so that's L, Earth Santa, is equal to 2/5 mass of the Earth with Santa and the radius of the Earth squared. Because we're at the equator, the distance from the axis of rotation to the equator is equal to the radius of the Earth. Doing a little bit of algebra, we get 4 pi over 5 TES times the mass of the Earth with Santa multiplied by the radius of the Earth squared is equal to our angular momentum with Santa. And we can simplify this then to find the time period, that's TES, so that's equal to 4 pi over 5 LES, where L here is the angular momentum, remember, multiplied by the mass of the Earth with Santa and the radius of the Earth. Now remember that LES here is equal to LE because we have conserved that angular momentum. So that gives us a time period then of 8.6164 times 10 to the 4 seconds. So that's around 86,164. As stated earlier on, the important value of how long it takes for the Earth to do one revolution, so one 360-degree turn, is 86,164 seconds. Now, we've just calculated our time value with the added mass on the equator. If we do the subtraction of these two values, we can find the difference between the two and therefore the difference in time with the added mass. This comes out to being around 2.2 times 10 to the minus 9 seconds, or 2 nanoseconds. So Santa would cause a slight increase of around 2 nanoseconds on how long it takes the Earth to do one full rotation, and therefore an extra 2 nanoseconds on the length of our day. Now this is a very small increase and is very menial realistically, but let's look at the difference if we were on the North Pole where Santa did decide to live. As I mentioned previously, the axis of rotation runs from the South Pole through the centre to the North Pole. So at the North Pole, if Father Christmas was to sit directly in the centre of the North Pole, the value of R would be very, very close to 0, if not 0. Which would mean the value of rotational inertia for Father Christmas on the North Pole would be near enough 0, and the value of angular momentum would be near enough 0, which would mean that there'd be no difference in the length of day if he did decide to live on the North Pole. So there we have it. The reason Father Christmas decided to live on the North Pole was because he would have no effect on the length of day, even though it's only a small effect on the equator. If he had a lot more presents to deliver, that effect might get bigger and bigger and bigger. And the reason he chose the North Pole over the South Pole, not really sure, might be a mystery. Could just be because a large amount of people live in the Northern Hemisphere, so he decided to join them living in the North Pole. So I hope you've enjoyed this little video on Santa, and you can now tell your friends why Father Christmas chose to live on the North Pole rather than the equator or elsewhere on the Earth. If you liked this video, please leave a like, comment and consider subscribing, and I'll see you in the next one.